Greetings, everyone. My name is Cláudio. I'm a doctorate student in Pontifical University of Rio de Janeiro under the orientation of Professor Luis Fernando Marta. This work is a report of the object-oriented programming architecture for the implementation of dynamic and nonlinear effects in structural analysis. This presentation is going to be divided in 4 topics. Firstly, a brief introduction, then the description of the UML class diagrams in 4 stages: static linear analysis, dynamic linear analysis, static nonlinear analysis, which is now under development, and dynamic nonlinear elastic analysis as an intention of future work. After that, a numerical example in the graphic user interface program will be shown in order to illustrate how the software works. Finally, conclusion and future works are going to be presented. The program treated in this work is called LESM, or Linear Elements Structure Model. It is an open source under development educational software for framed structure analysis. It has been developed at the Department of Civil and Environmental Engineer of Pontifical University of Rio de Janeiro and targets at graduate and undergraduate engineering students. It includes a graphical user interface, and it's designed based on object-oriented programming paradigm, based on the idea of classes, data abstraction, encapsulation, polymorphism, and inheritance. This paradigm makes the software understanding easier for the users and has proven to be beneficial in the matters of maintenance and further updates. The program is developed in a MATLAB environment, which provides a high-level programming language as well as an extensive library of predefined functions, favoring its understanding even for those who are rookies in any type of programming language. Firstly, LESM was developed to perform linear elastic analysis of 2- and 3-dimensional linear elements model, such as frames, trusses, and grillage, using the direct stiffness method. Secondly, an extension with dynamic analysis is incorporated in the software, which was possible due to the object-oriented program architecture, with a receptive environment for updates. A nonlinear analysis is now under development with the increment of more classes and methods. The main objective of this work is to report the actual state of the software, detailing the architecture adopted, the changes made from a previous version, as well as future works. Also, a numerical experiment of dynamic analysis is shown. This is the class diagram of the static linear elastic analysis of LESM. The objective here is to briefly describe the classes that are responsible to the composition of this first version of the software, starting with the A&M class. The A&M class is the analysis model class. It is an abstract superclass that generically specifies an analysis model in the program. This superclass declares abstract methods that define the generic behavior of an analysis model. These methods are the functions that should be implemented in a subclass that deals with specific types of analysis, such as 2D truss, 2D frame, grillage, 3D truss, and 3D frame. The node class is a class that defines node objects in the program. A node is a joint between 2 or more elements or any element end. Use it to discretize the model. It's always considered as a 3-dimensional entity, which may have applied loads or prescribed displacement. The section class is the class that defines the cross-sectional objects. All cross-sections are considered to be of a generic geometry, which means that their shape are not specified, only their geometry properties, such as area, moment of inertia, and height. The material class defines the material objects. All materials are considered to be homogeneous, isotropic, and have linear elastic behavior. The RSR joint is a class that generically handles 3D behavior of semi-rigid joint. The element class is a class that generically handles a 3-dimensional behavior of a linear element. 2 different subclasses specify the element flexural behavior: Timoshenko, in which the shear deformation is considered, and Euler-Bernoulli, that is assumed that there is no shear deformation. The formulation of Euler-Bernoulli is also known as a Navier element, so in other words, Navier element. The LESM class is the load element class that defines an element load object that's responsible for defining the response of a linear element to load effects, such as the computation of element fixed end forces, element equivalent nodal loads, and element internal displacements. Also, two different types of flexure behavior are considered, the Navier and the Timoshenko. The DRV class, or driver class, defines a driver object that's responsible for running the functions that drives the structural analysis. In the new version with dynamic analysis, changes due to the program structure were made, and this will be discussed later in this presentation. But all properties related to model information were moved to a new class called model. The second type of analysis treated here refers to dynamic linear elastic analysis. In this analysis, the dynamic motion matricial equation must be satisfied. By looking at the left-hand side of the equation, the first term refers to the inertial forces, where m is the mass matrix and x2 dots is the acceleration vector. The second term are the damping forces, defined by the damping matrix C and the velocity vector x dot. The third and last term of this side is a vector of elastic forces defined by stiffness matrix K and the displacement vector X. The equality with the dynamic forces applied must be satisfied. The displacement vector can be separated in two parts. One related to free vibration and described by an homogeneous solution, and other related to the forced vibration and described by a particular solution. The major changes made in LESM diagram to include the dynamic analysis in its previous version are going to be treated here. Firstly, as I commented before, the model class was created to handle all the information that characterizes the structural model, and the driver class was adopted only to manage a different type of analysis. A solver class was created to handle numerical methods called by drivers, and a new load function class was created to handle transient load patterns for dynamic analysis. For transient numeric integration, time integration methods need to be implemented. So Newmark, Wilson theta, three-step Adams-Moulton, and fourth order Hunch-Coulter were the methods that were chosen to be implemented in this work. This is the dynamic linear elastic analysis class diagram of LESM. It's important to note that the previous version classes are colored with blue color, and the new classes implemented for dynamic linear analysis are colored with this red color. Firstly, it's important to note that the class DRV, or driver class, is now with the responsibility of being a superclass of the analysis type. So all properties related to model information were moved to a new class called model, as it was said before. A result class defines an object that is responsible for storing results after data is processing by a DRV object. It's now coupled here. Now, the driver class has two subclasses, driver LES and driver LED. The LES deals with linear elastic static analysis, and the LED deals with linear elastic dynamic structure analysis. The solver is an abstract superclass with methods that will be implemented in the subclasses according to the analysis. Here we have the LES that deals with linear elastic static analysis, the AM3 that deals with the third order Adams-Moulton numerical method, the model sup that deals with elastic dynamic analysis, solving an uncoupled system of ordinary differential equations in a model space, the Newmark that deals with Newmark methods, RK4 deals with Range-Kutta fourth order method, and Wilson that deals with Wilson theta. Also, the load function that was commented before is a superclass that defines load functions objects. Load functions describes the behavior of load values throughout the analysis interval. The subclass related are static load functions. That is, the load value will stay always the same, although it occurs in a determinate time interval. Slope load function considers a linear variation of the load through the time, and a periodic load function that is described by a cosine function. The third type of analysis treated here in this work is static nonlinear elastic analysis. In a geometric nonlinear analysis, the deformed configuration of the structure must be taken into account when solving the equilibrium equation. For that, iterative methods that update the deformed configuration and by consequence the internal force and stiffness matrix need to be implemented. In this equation, dF represents the incremental nodal loads, d delta represents the incremental nodal displacements, K is the elastic stiffness matrix, and Kg is the geometric stiffness matrix, which represents the change in structural stiffness due to update of incremental load and consequently geometry change. These updates are under development in the software. A subclass DRV NLES is created, a solver NLE is created, and numeric methods, iterative methods are implemented. Those methods refers to load control method, the work control method, the cylindrical arc length increment, minimal norm solution, orthogonal residual strategy, and general displacement. This is the third diagram that is shown in this presentation. It's related to static nonlinear elastic analysis. It can be noted that the new classes related to this analysis are colored with green. These formulations are under development. All of the methods are already implemented in an object-oriented paradigm, but it still needs to be coupled in the graphical user interface software LESM. So it's an under development project. Still, we can show what are the classes and the subclasses that involve this kind of analysis. So a new superclass solver with the objective of being the superclass of the subclasses of nonlinear analysis is created, and the solvers, the subclasses with specific methods are also implemented. So here we have LCM, WCM, all LCM, MMCM, ORCM, and GDCM. Those classes refers to load control methods, word control methods, cylindrical arc length, minimal norm solution, orthogonal residual strategy, and general displacement, respectively. Also, as the software is implemented in MATLAB language, the solver EIG is already available. However, if the software is going to be developed in a lower level language, classes for solving the eigenvalue problems need to be implemented. So they are showed here. The fourth type of analysis treated here is the dynamic nonlinear elastic analysis. It's expected as a future work to implement this kind of analysis, coupling the solutions that are already implemented here. In order to adequate the diagram for further implementations, following what was already done for the nonlinear elastic analysis, new solver needs to be implemented. Also, a new driver methods, a new driver subclass needs to be implemented. Here it's possible to see where those classes referring to this fourth kind of analysis, which is the dynamic nonlinear elastic analysis, would be in our class diagram. So this is the graphic user interface. The structure here is already modeled to save some time. So the materials, cross-sections, and elements and nodes are already defined. The analysis type will be the dynamic. Here we have the options dialog. You can see that the methods here are implemented. I'm going to control the node 13 in the degree of freedom dy 0.01 meters and 5,000 steps during 5 seconds. This is going to be our analysis. So now process data. Take a little, and then you can display the vibration modes. Here you can see vibration modes. First, of course, all vibration modes, the same number of degrees of freedom. Also the dynamic deformation as a displacement in the top node and the vibration. And here are the dynamic results. You can see the degree of freedom, the displacement, the response, the acceleration response. This is the dx, if we can see the dy here. This is the phase portraits. So, see, and that's it. The model in a object-oriented program. This was the dynamic analysis. We have the static analysis, 3D trusses, 3D frames, and it's very easy to use, but the focus here is only to show a little bit of the software. As conclusions and extensions, summarizing the whole work, the objective here was to detail the class diagram of the under development software LESM, showing that a modular object-oriented programming is a clever way to organize the program. Also, it makes it easier to understand and more receptive for future updates. A nonlinear analysis is currently under development. And as future works, models related to nonlinear dynamic analysis, still structured design, which is already under development, structural optimization, and sensitivity analysis intended to be implemented and coupled with the diagram of this work. Those are the references consulted for this work. And I would like to thank the institutions and thank you all for watching.